Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
All right, welcome to our Week 7 Explainer. This is part 1, where we're going deep on the concepts that power modern AI. We're going to start with the core idea of attention and build all the way up to the transformer architecture. Yeah, the engine that pretty much changed everything.
So to really get why attention was such a massive breakthrough, you have to understand the problem it solved. On the left, you see a classic recurrent neural network, or RNN. To understand a long sentence, it had to literally cram the meaning of every single word into one single vector. This created a huge information bottleneck. I mean, by the end of a long paragraph, the model had totally forgotten what it read at the beginning. But now look at the right. The attention mechanism creates these direct connections, like superhighways, from the output all the way back to every single input. No more bottleneck. It has direct access to everything all at once.
And that really was the fundamental challenge, right? AI had a serious memory problem. How could it possibly process these long sequences of text without forgetting the crucial details from the start? Solving this wasn't just about a better model. It required a completely new way of thinking about the problem. So instead of thinking about memory as, a single compressed file, the innovators behind attention came up with this amazing analogy. They started thinking about it like a special kind of database, a database for ideas, where the model could look up relevant information whenever it needed it. Okay, now this slide is so cool because it really frames the whole concept. A normal SQL database, right? It does a hard lookup. You send a query like Lynn, and you get one exact match back for the value mu. It's super rigid one-to-one. But neural attention, well, it's soft. You send a query, and instead of just one answer, it looks at all the available keys, figures out how relevant each one is, and then gives you back a weighted sum, a blend of all the values. It's not just one piece of info. It's this rich cocktail of all the most relevant stuff. So to make this database idea actually work, we need 3 things. Think of it like a smart filing system. The query, Q, is what you're looking for right now. The key, K, is kind of like the label on each file folder. And the value, V, is the actual good stuff inside each folder. Attention is just the process of using your query to check all the key labels to figure out which folders, which values, are the most important ones to pull from at that exact moment. Okay, so we've got the concept, this cool differentiable database. But how do we actually build the thing? How do we turn this neat analogy into a mathematical function that a computer can actually run and, more importantly, learn from? And this diagram just beautifully lays out the process. It's like a 3-step dance. First, you take your query and you compare it to every single key you've got using a score function. This just tells you how well they match. Second, you push those scores through a softmax function, which turns them into what we call attention weights. They're basically just percentages that all add up to 1. This tells the model how much attention to pay to each item. And third, you multiply those weights by their matching values and sum it all up. What you get is your final output, a brand new vector totally packed with context. Now that score function we just talked about, it's evolved. The original version, back in 2014, was called additive attention. It was powerful, for sure, but it was also kind of slow and clunky. The real game changer was scaled dot product attention in 2017. That was the rocket ship. It was so incredibly fast and efficient, and honestly, it's what made the massive scale of today's transformers even possible. So why is it so good? Well, at its heart, it uses a dot product, which is just a super fast way to measure how similar 2 vectors are. But the real magic, the secret sauce, is in the scaling, that little division by the square root of d. See, without it, the dot products can get huge, which pushes the softmax function into a state where it just stops learning. The model gets stuck. This tiny scaling trick keeps all the numbers in a healthy range so the model can keep learning effectively. It's a tiny detail with absolutely massive consequences. Okay, let's take this to the next level. What happens when we take this powerful attention mechanism and we turn it inward? What if a sequence of words starts paying attention to itself? This is self-attention. Instead of a query coming from somewhere else, here, every single word in the sentence generates its own query, its own key, and its own value. Then, every word gets to look at every other word in the sentence, including itself, all at the same time. This creates an unbelievably rich, contextual understanding of the sentence, where the meaning of each word is shaped by its relationship to all the others. But why stop at just one perspective, right? That's the whole idea behind multi-head attention. Instead of doing self-attention just once, we run a bunch of self-attention layers, or heads, in parallel. And as you can see in these diagrams, each head learns to focus on different kinds of relationships. Maybe head 1 is tracking grammar, while head 2 is tracking what the words actually mean, and head 3 is looking for connections across the whole sentence. It's like having a whole team of specialists analyzing the sentence all at once.
There is one little catch, though. Because self-attention looks at all the words at the same time, it's kind of like you just threw them all into a bag. It loses the original order. The model would have no idea what the difference is between dog bites man and man bites dog. So to fix this, we inject a little piece of information about the position of each word. It's called positional encoding, and it acts like a little GPS signal that tells the model exactly where each word was in the original sentence.
So there we have it. We have our key components. We have an efficient way to score attention. We have the idea of self-attention, the power of multiple heads, and a fix for the word order problem. Now, let's put it all together.
And here it is, the transformer. If you look closely, you'll see all the pieces we've just been talking about. The inputs come in at the bottom left, and the very first thing we do is add that positional encoding. Then the data flows right into our multi-head attention block. This whole stack on the left is called the encoder. It just chews on the input and builds a really rich understanding, which it then passes over to the decoder on the right side to generate an output. This is the blueprint for basically every major large language model we have today.
So to wrap up part 1, let's just quickly recap the journey. We started with the core idea of attention as a soft database lookup. We made it super efficient with scaled.product. Then we gave it a bunch of different perspectives with multi-head attention. And finally, we put all those parts together to build the transformer, one incredibly powerful system.
So we've built the engine. The big question is, what are we going to power with it? This single architecture became the foundation for models that would literally change the world. In part 2, we're going to explore those legendary models like BERT and GPT that were built on this very foundation. We'll see you there.